So, we are gradually inching towards the end of the course, possibly 3 more lectures in which the course would be ended, taking into this lecture, taking into account this lecture. So, I would be having this and 2 more lectures to go, and the last one would be a overall summary of what we done and what you can do from them, showing you some references again. So, what is important here to note that at the end of this long journey, we are taking some detours. Here we are not following a very fixed pattern or syllabus of some institute or university, so that you can do well in the exams. This course is not for those who have some course in convex optimization, or they have a course in optimization in general, but this course is for those who would use convex optimization in their work, could be engineers, and also for those who would possibly like to take up this subject as their future choice or as a hobby. Whatever you do, when you take a trip anywhere in the world, then it is very important that you also take a detour. You just do not go and see a place, you also go and see neighbor places in the neighborhood. So, what we are doing now is like seeing places in the neighborhood, taking detours, doing echelon variation principle, trying to understand how to characterize approximate minima, then trying to understand what do you mean by descent direction of descent when the function is non-smooth. So, once we have an idea of direction of descent, we will go to something more else. Basically, there are a lot of sweets or nice food, and we are just tasting a bit of each. So, what happens is the following, that after this we are going to look at how the tools of convex analysis can be used for non-convex functions, to study non-convex functions, which are representable in some sense by convex functions. For example, we will talk about the maximization of a convex function, which is actually a non-convex problem. It is a minimization of a convex function, which is a convex problem. The maximization of a convex function over a convex set is a hard non-convex problem, because for a convex function, a global maxima and local maxima are not the same. We will show by very simple examples, and that immediately it makes it a very difficult problem. So, now what do we mean by descent here? So, if f is differentiable, then let us recall what would happen. By a descent direction, we mean a direction d in Rn such that f of x plus Td. So, it is the descent direction at x, that is we are moving from the point x, is strictly less than f of x for t greater than 0 and sufficiently small. In the sense that, okay, if I move a little bit in that direction, this is not really a correct way to say it, for t greater than 0, for some t greater than 0, that would be a better way to say. So, what I am doing is that if I have x here, I try to move in a direction d, and I not only move in a direction d, suppose I move a direction Td, then here is my x, then this point would become my x plus Td, and I really want to know the function values. I want to know that the function value here is strictly smaller than the function value here. So, I have, by moving along this direction, I have made an improvement in the function value if, because we are essentially concerned about minimization. So, essentially we are looking for minimizing a convex function f over R n at this moment, unconstant minimization, where f is of course of this type. So, we have already seen that if f is differentiable, then there could be a verifiable condition. There could be a verifiable condition in the sense that if f is differentiable, convex function. I will use these sort of shortcuts, you would get habituated to it, or you have already got habituated to it. So, if f is a differentiable convex function, then any d which satisfies strictly less than 0, any d which satisfies this is a direction of descent at x. Now, look at the scenario when it comes to the non-smooth case. Here we do not have a derivative, so we cannot speak of things like this, but we can always possibly try to use the directional derivative, because if the convex function is differentiable, the directional derivative is equal to this. So, now let us consider a convex function f such that 0 is not element of del f x. So, from x, so x is not a minimizer. So, we can make progress from here. So, how do you do that? One way is to assume that to imitate this fact, let T be element of R n such that the directional derivative of x in the direction d is strictly less than 0. Then we will have, by definition of directional derivative, limit t going to 0 from the positive side, one sided directional derivative f of x plus t d minus f of x by t strictly less than 0. This simply shows that for t sufficiently small, I am not going into the details of the argument. Those who are mathematicians who can immediately figure out what I am telling. Those who are engineers, just go back to your basic calculus course, and then you would recognize there is a basic fact that there is, if limit f x, x goes to a is equal to L and L is strictly less than 0, then in a there is a neighborhood of a without the point a, there is a punctured neighborhood of a in which for every x the function value of f x is strictly less than 0 2. So, the similar same way we are writing it in a informal fashion, which is done in advanced mathematics. For t sufficiently small, we have f of x plus t d. So, this would imply that d is a descent direction. So, if D is a descent direction, there is also, because of the fact that there is a relation between the subdifferential and the directional derivative, which says in fact it is max this would simply imply that if D is a descent direction, then V of D would also be strictly less than 0 for all V element of del f x. Of course, this is possible because of the compactness of del f x, which is a compact convex set. So, there would be a V in here such that V of D would be this and this would be strictly less and hence the rest of them. Now, this is quite different from grad f is strictly less than 0. You observe that if f is differentiable, then this condition of descent, condition D, then D is nothing but the standard condition in the differentiable case. Okay. Once this is done, let us draw some little pictures to have an idea what does a descent direction means. So, let me collect the set D such that V D is strictly less than 0 for all V element of del f x. So, this is called the descent direction, set of descent directions at x. Of course, we can also write dx is a set of D such that f dash x d is strictly less than 0, they are the same thing. Now, what does this tell me? That what sort of a set is this? This is an open set, because this is a continuous function. Since this is a continuous function, if I take the complement of this set, this is a complement of this set for which this is not satisfied, but dCx is closed because this is a sublinear function in D, a convex function in D, the directional derivative which we have learnt earlier. So, this would imply the first property is as D of x is open. Number 2, D of x is a cone, an open cone with 0 as the vertex, but of course, 0 is not an element of that cone, because if 0 is an element of this cone, then this will not be satisfied. So, this is because this happens because f dash x d is positively homogeneous in D. Since f dash x d is plus positively homogeneous, that is D element of dx would imply lambda d element of dx for all lambda greater than 0. But we should also remember that dx is a open is a convex set also. So, what we have essentially is that dx is an open convex cone. Now, let us draw a picture about a point x which is not optimal, and we are basically looking at the sublevel set of that. This is not optimal, then we are trying to look at x for which f of x is less than this. So, the optimal lies here. So, it is not the optimal. So, this set is a sublevel set of f. So, we will denote it instead of this cumbersome notation, we will denote it as level S of f x for the moment, or just L if you want. Now, what would happen is, if you have the del f x here, assume the del f x looks like this. So, basically draw perpendiculars here. So, first draw perpendiculars at this point, draw tangent sort of thing, draw the tangent cone at this point. So, this would be nothing but the tangent cone to the level set at x. And once you have drawn the tangent cone, the idea is that on this you draw the perpendicular. Product with this line is 0. So, the del f x is a compact convex set like this. Now, you observe very clearly that if you take any direction d in the interior of this particular cone, and if you take any direction here, because this perpendicular line is the separating lines. So, if you take any direction here, their angle they will make is always obtuse. So, the direction of dx is also the interior of the tangent cone to the lower level set at lower level set S f x at the point x. So, this is also another interesting representation or a geometrical representation of the set of descent directions. So, here is the geometrical picture. So, if x is not an optimal solution, this is the way, this is how the sublevel set would be related to the subdifferential set. So, this is an interesting picture and one has to keep that in mind. But what there is another way of looking at it also, because you see what is happening is that if basically what you want is to find a point. So, the goal is this: find an x such that this happens, but it is not so easy to find an x. Suppose you find an x for which this is your d f x here. So, this is your del f x, but 0 is not, 0 is here. So, what you have to do is, for example, here you draw in this case, which is a nice looking del f x. So, you find the distance between 0 and del f x, and you observe that take this direction and take any element, take the inner product with any element here in the del f x, there will be the angle would be obtuse, the inner product would be strictly negative. And so, this itself, this distance can be also viewed as a direction of descent. So, what is this? Basically, this is how this direction is generated, that you take a hyperplane which is strictly separating 0, and basically you take a hyperplane which is perpendicularly cutting this distance, then that distance, right, is the distance that hyperplane will generate this direction d, because that hyperplane would generate this direction d, because that this direction d is perpendicular to this hyperplane. So, this direction d is also similarly a direction of descent. So, unlike the case where you have a smooth situation, or then in that sort of situation, in there is only one way to talk about a descent direction. Here there are many very different geometrical approaches, many different approaches to talk about the descent direction, and this is a very important way to talk about the descent direction, because here, for example, there is a very simple result which says the following. There is a theorem for this from this famous book by Hiriya-Turuti and Lemma-Rachel. It is a classic actually. Convex analysis and minimization algorithms, Springer 1993. If I am not wrong, it is 1993. I will just check it out and tell you in a minute. Sorry, its second printing is 1996. The first printing was 1993. So, these are the authors, and it is a theorem from their book which says a descent direction is a direction d such that if alpha is element of you have to figure out that this is non-empty. Obviously, because it is a descent direction, f dash x d is strictly less than 0. So, I am basically then taking this interval. In the hyperplane, this hyperplane separates del f x. So, obviously, here x is not a minimum thing, del f x is not equal, does not contain 0 and 0 strictly. And that is S of d is less than equal to alpha strictly less than 0 for all s element of del f x, which is very natural, because from the definition of the directional derivative or the descent direction, if d is a descent direction, this would happen. And then if I define a separation hyperplane like this, then this is a strictly separating hyperplane, just if you know the language of strict separation. Now, when we are trying to solve a convex problem, basically they will devise an algorithm. We want that if I am at x, I should be able to move in a direction d till my function value keeps on decreasing, but I cannot move very little. I should try to make a quite a good move, so that I move quite far off from x, more towards the optimal point, and my function value decreases. So, this is the standard optimality condition which we will use. X is minimum if and only if f dash x d is greater than equal to 0 for all d in Rn. This is a standard optimality condition. If you have not forgotten it, just go and try this as homework. Now, once this is done, what we have is the following. This would imply that if x is not a minimum, there exists d element of Rn such that f dash x d is strictly less than 0. So, there exists a direction d for which this is strictly less than 0. So, in effect, what I have to do is find such a d for which the value of this is minimum. Among all such f dash x d's, I will take the minimum value. So, the difference that I will get between f of x plus t d and f x would be quite large. That is, f of x plus t d would provide a very heavily improved value of f, that it will be truly a descent. Now, thus in order to do so, now we define what is called the normalized steepest descent direction problem. The normalized steepest descent direction of f at x associated with on any norm, just take Euclidean norm for simplicity. Is a solution of the problem of the convex problem. So, in order to solve a convex problem, we are actually solving another convex problem. And we can of course take, because we have normalized norm d equal to 1. So, this will be a compact set over which we are minimizing a continuous function. You can also take norm d less than equal to 1, does not matter. So, you can basically, this problem is equivalent to the problem this and this and this two problems are same. So, it can be also thought of what as a mean max problem. Now, this idea can lead us to what is called the steepest descent method for non-smooth convex functions. Steepest descent method for non-smooth convex functions. So, let us go do this algorithm step by step. This is also from Hiriart-Ruti and Le-Marchal. Step 1 is the basic stopping criteria. So, we start from the kth iteration itself, becoming slightly more writing in a more general way, which you can understand. So, all this is to give you the flavor of research in convex optimization, because the basic idea of the course really ends with a basic idea of semi definite programming and that of interior point methods in linear programming. So, here what we are doing, this taking these little detours, is to give you the flavor of research in this area. If then stop, then xk is the solution. If not, then do something. If not, then find dk by, I can call the NS problem, normalized steepest descent, or NSD, by solving NSD. They are the same problems. Now, you have to find a step size Tk, which is step 3. Find Tk greater than 0. So, you have to find the descent direction which gives you the minimum value of this. So, along that descent direction I will have to move, because I am taking the minimum value of this one. So, it will be the minimum negative number. So, it will be quite far from 0. So, the difference between the two, this f of x plus T d minus f x would be quite highly negative. So, then actually f x would be quite bigger than f of x plus T d. So, we would have made a good movement. So, f of x dash d strictly descent direction does not mean that this will be means it is enough to have a descent direction. It is good to have a normalized steepest descent direction. That is where the drop of the function value would be the steepest, such that f of now this is nothing but what we write as xk plus 1. Oh, sorry, I have made a blunder, not a blunder, but blunder in the sense that I always mentioning that whenever there is a vector, I should put the subscripts on the top, and whenever there is a scalar, the subscript is on the bottom. So, this is xk plus 1, this whole thing is written as xk plus 1, xk plus 1 is xk plus tk. Step 4, replace k plus 1 by k, go to step 1. So, here, so what we did today gave you a fairly good idea about developing a small algorithm, whether it runs good or not. All these things are very, very different issues, right. If it is not doing so, whether it is running good or whether it is running fast, quite fast or quite slow, that sort of things we are not giving. We are telling that even in this difficult situation where we do not have the derivative, we can still build up an algorithm which is meaningful. You can obviously develop convergence rules for this, which we will not get into. So, our job now would be to give you a idea of what we would discuss in the next lecture is how to use convex functions in non-convex optimization, how to use convexity in non-convex optimization. There could be convex optimization problems made out of non-convex optimization problems made out of convex functions. For example, you consider the problem to minimize x where hx is equal to fx minus gx. This is a DC function, but this is called a difference of convex function if fx is convex and gx is convex. There are many problems which are of this type, fx minus gx. For example, if you have any problem of this sort, if suppose hx is of the form if this is convex, then again h is a DC or difference convex problem, DC function. So, in this case h is called DC, DC is the short form of difference convex. So, but here the components are convex functions. And so, I can use ideas from convexity to tell something about this problem, which by itself is a non-convex problem because the difference of two convex function is not convex. H is called a DC function, note that H is not convex. Of course, our idea would be tomorrow to show you what sort of areas DC functions arise, some one or two examples, and then we are also going to discuss a very important class of problems. People can ask, oh, you are talking about minimization of convex function, minimization of convex function. What is the great thing about minimization? Why not maximization? Aren't they the same thing? Aren't max of fx is minus mean of minus fx? I said yes, that is fine, but there is a crux because non-differentiability brings in a lot of issues, and the nature of convex function also puts into us a lot of problems. So, if you take max of fx over x element of C. So, here I am not talking about minimization, but I am talking about maximization. This is a convex function, this is a convex set. What I have here, look at the problem like this, which will be minus 1 and plus 1, where the problem is say here it is a continuous convex function, but you see here plus 1 is a C, if C is equal to minus 1 plus 1, minus 1 is a local maxima, plus 1 is where the global maxima is attained. So, global maxima is not equal to a local maxima. Local maxima does not imply global minima, global maxima. Local maxima for this problem does not imply global maximum. Thus, it is a hard problem. Any problem which where a local minima is a global minima or a local maxima is a global maxima is a soft problem or a simpler problem to or tractable problem. It is a convex minimization where you have local minima as a global minima, but for convex maximization local maxima is not a global maxima, because here essentially what is convex function? You are talking what is max of f x is minus mean of minus f x. So, this problem can be stated as mean of minus f x x element of C, but minus f x is not a convex function, it is a concave function. You are talking about the minimization of a concave function which is a non-convex function, and hence the max of maximizing a convex function over a convex set is a highly non-convex and difficult problem. The problem is that the interesting part that we will discuss tomorrow is that we can handle these class of problems using the tools of convex analysis, and that will be a very beautiful thing to see. Thank you very much.